The fundamental process of substitution for definite integrals. Okay, let's begin with slide 1, the fundamental process of substitution for definite integrals. Welcome. In our journey through calculus, we've already learned how to tackle some definite integrals using straightforward formulas. However, as we progress, we'll inevitably encounter integrals that are, well, a bit more challenging. These integrals often appear too complex to solve directly with the basic rules we've covered so far. That's where the method of substitution, sometimes also called change of variable, comes in. Think of it as a tool in our calculus toolkit that allows us to reshape these complicated integrals into something much more manageable. The main idea is this. We want to take a complicated integral, written as the integral from a to b of f of x with respect to x, and I'm saying f of x to represent a function of x, and, with respect to x, to indicate we are integrating with respect to the variable x, and transform it into a simpler integral. We do this by introducing a new variable, which we'll typically call u. The simpler integral will look like the integral from c to d of f of u with respect to u. So, we're essentially swapping out x for u, and changing the limits of integration accordingly. Now, this might seem a bit abstract at first, but it's deeply connected to something you already know, the chain rule from differentiation. In fact, the method of substitution is essentially the chain rule working in reverse. We'll see how that connection becomes clearer as we work through examples. In the following slides, we'll break down exactly how to identify when substitution is useful and the step-by-step process to apply it. So, let's move on to understanding the core logic behind this powerful technique. The core logic, the function derivative pair. The first point here says, the secret to successful substitution is identifying a specific relationship within the integrand. What does that mean? Well, it means you need to look at the function you're trying to integrate and see if there's a hidden pattern. Specifically, you're looking for a pair, a function and its derivative. Think back to the chain rule in differentiation. Substitution is essentially reversing that process. Now, this is where it gets a little more specific. The slide explains that the substitution method is particularly useful when you have an integrand that's a composition of functions. A composition of functions just means one function inside another. We often write this as f of g of x, so imagine a function, g of x, and then f acting on the result of g of x. And crucially, if the derivative of the inner function, that's g prime of x, is also present as a multiplying factor in the integral, then substitution is a great approach. Let's look at the mathematical representation. We have the integral from o to b of f of g of x, multiplied by g prime of x with respect to x, so that's integral, limits from a to b, of f of g of x, times g prime of x dx. Now here's the key step. We make a substitution. We let u equal a g of x. This is where we introduce our new variable. And because u equals g of x, that means the differential do, which represents an infinitesimally small change in u, is equal to g prime of x times dx. Remember from your calculus basics that do is simply the derivative of u with respect to x, multiplied by dx. Finally, this substitution transforms the original integral into a much simpler form, the integral from g of a to g of b of f of u with respect to do. So, integral, limits from g of a to g of b of f of u do. Notice how we've replaced everything in terms of u and do. Okay, so let's move on to slide 2. This slide really gets to the heart of how substitution works. As we discussed on the previous slide, substitution is about simplifying integrals that are a bit too tricky for our basic rules. This new integral, hopefully, is something we can solve using our standard integration techniques. We'll see how to actually do that in the following slides, but this slide is about understanding when and why substitution works. Remember, identifying that function derivative pair is the first and most important step. Step-by-step process of substitution. Okay, so we've discussed why substitution works. It's essentially reversing the chain rule and what we're looking for, that function derivative pair. Now, let's solidify how to actually do substitution. This slide outlines a step-by-step process to make sure we approach these problems systematically. First, step 1, identification. This is arguably the most crucial step. We need to carefully scan the integrand, that's the function inside the integral, and look for a part of it whose derivative is also present in the expression. Think of it like a puzzle. We're looking for pieces that fit together. Often, and this is a helpful tip, the inner part of a composite function is a good place to start. What do I mean by inner? Well, if you have a function inside another function, like something inside a square root, raised to a power, or within a trigonometric function, that inner function is often our candidate. Now, step 2, assignment. Once we've identified that part, we assign it a new variable. We usually use u, but you could also use t or any other variable, really. The important thing is to be consistent. So if we decide that g of x is the part we want to substitute, we simply write u equals g of x. Remember, g of x means the function g applied to x. Next, step 3, differentiation. This is where our calculus knowledge comes in. We need to find the derivative of u with respect to x. We write that as du by dx, and that equals g prime of x. G prime of x is just the derivative of the function u with respect to x, but we're not quite done yet. We need to rearrange this equation to express dx in terms of du. This is a simple bit of algebra. We just solve for dx, and we get du equals g prime of x times dx. This is extremely important because it links our new variable, u, back to the original variable x. Moving on to step 4, transformation. This is where we make the actual substitution. We replace every instance of x and dx in the original integral with u and du, respectively. The goal here is to completely eliminate x and dx from the integral. If you still see x hanging around, you haven't fully substituted. Finally, step 5, simplification. After the transformation, the integral should now be in a much simpler form, one that we can solve using the basic integration rules we already know. It might look completely different from the original integral, but that's the point. We've transformed it into something manageable. Remember, we're not actually solving the integral on this slide, we're just setting ourselves up to do so. We'll cover the actual integration and dealing with the limits of integration in the next sections. So to recap, these 5 steps, identification, assignment, differentiation, transformation, and simplification, provide a structured approach to tackling integrals using substitution. Keep these steps in mind, and you'll be well on your way to mastering this powerful technique. Conceptual example. Okay, so now that we've discussed the why and the how of substitution, let's solidify our understanding with a concrete example. This slide walks us through a problem step by step. We're asked to evaluate the definite integral of 2x times e to the power of x squared, with the limits of integration from 0 to 1. Let me write that out verbally. Integral from 0 to 1 of 2x times e raised to the power of x squared, with respect to x. Now remember from the previous slides, the key is to spot that function derivative pair. Step 1, identify the pair. Looking at the integrand, that's the part inside the integral, we notice the function x squared in the exponent. And crucially, the derivative of x squared is 2x, which is also present in the integrand, multiplied by the exponential function. This is fantastic. It tells us substitution is a viable approach. We have our function and its derivative nicely lined up. Step 2, assign the variable. This is where we introduce our new variable. We'll let u equal x squared. This is a simple assignment, and it's the foundation for the rest of the process. Step 3, find the differential. Now, we need to connect the change in u to the change in x. We differentiate both sides of our equation, u equals x squared. With respect to x, this gives us du over dx equals 2x. Think of it as applying the power rule. Then, to get du by itself, we rearrange the equation to say du equals 2x dx. This is extremely important. We're not just replacing dx with du, we're replacing 2x dx with du because of the derivative. Step 4, transform the integral. This is where the magic happens. We substitute. We replace every instance of x squared with u, and we replace 2x dx with du. So the original integral, the integral from 0 to 1 of e to the power of x squared times 2x dx, transforms into the integral from 0 to 1 of e to the power of u do. Notice how we've eliminated all traces of x from the integral, and now it's entirely in terms of u and do. Step 5, final integration. Now, the integral of e to the power of u is simply e to the power of u plus a constant. See, this is a standard integral you should have memorized. Now, a quick note. In this introductory section, we're focusing on how to perform the substitution and transform the integral. We're not yet dealing with evaluating the definite integral by applying the limits of integration. That's something we'll cover in the next section. For now, the goal is to master this transformation process. This example should give you a clear, step-by-step understanding of how substitution works. We'll be practicing this technique with more complex examples soon, but this is a solid starting point. Real-world analogy, the currency converter. Okay, let's move on to a real-world analogy to help solidify our understanding of substitution. This slide uses a familiar scenario, international currency exchange. Think of substitution like using a currency converter when shopping internationally. This is a great way to visualize what's happening mathematically. Imagine you are looking at a price tag in Japanese yen, that's JPY, but your bank account and budget are in US dollars, that's USD. Now you can't directly subtract yen from dollars, can you? It just doesn't make sense. They're different units. To make the calculation possible, you use a conversion rate, and this is the crucial part. The conversion rate acts like the derivative, which we denoted as du over dx in our previous slides. It's the factor that allows us to transform the price from yen into dollars. So, we multiply the price in yen by the conversion rate to get an equivalent value in US dollars. Once the price is in a currency you understand, US dollars, the subtraction, which represents the integration process, becomes simple. You can now easily determine if you have enough funds to make the purchase. Once the transaction is done, you have effectively solved the problem by changing the variable of the currency. We started with a price in yen, converted it to dollars, and then performed our calculation. Similarly, in substitution, we change variables within the integral to make it solvable. This analogy highlights that substitution isn't about changing the value of the integral, but rather about expressing it in a more convenient form, a form that allows us to actually solve it. We'll build on this understanding as we move towards applying limits to complete the definite integral calculation in the next sections. Key takeaways. Okay, let's recap the key takeaways from the substitution method, as we've discussed it so far. This slide summarizes the most important points to keep in mind as you practice. First, the purpose of substitution is to take a complicated integral, one that's difficult to solve directly, and transform it into a simpler, standard form that we can integrate using our basic integration rules. Remember, we're not changing the value of the integral, just its appearance to make it easier to work with. Next, the trigger. This is how you know if substitution is a good idea. You need to scan the integrand, the function inside the integral, and look for a specific pairing. You're searching for a function, let's call it g of x, and its derivative, g prime of x, both present within the integral. If you see a function nested inside another function, a composite function, and the derivative of the inner function is also hanging around as a multiplying factor, that's a strong signal that substitution might work. Now the goal. Once you've identified that function derivative pair, the aim is to completely eliminate the original variable, x, and its corresponding differential, dx, from the integral. We want to rewrite everything entirely in terms of our new variable, u, and its differential, do. This is crucial. You can't have both x and u lingering in the same integral. Finally, the relationship. This is the heart of the substitution process. It's based on the fundamental principle that the differential do is equal to the derivative of our substituted function, g prime of x, multiplied by dx. So, do equals g prime of x dx. This relationship is what allows us to replace dx with do and successfully change the variable of integration. Keep these 4 points in mind, and you'll be well on your way to mastering the substitution technique. In the next slide, we'll look at some common mistakes students make, so we can avoid those pitfalls as you begin to practice. Common mistakes to avoid. Okay, let's move on to the final slide, where we discuss some common pitfalls to avoid when using substitution. It's really important to be aware of these so you don't lose marks on your exams. 1. Ignoring the differential. A very frequent mistake I see students make is simply replacing dx with do without properly accounting for the derivative. Remember, dx is not equal to do. They are related but not interchangeable. When we make our substitution, let's say we set u equal to g of x. We find that do is equal to g prime of x times dx. So, dx is actually equal to do divided by g prime of x. You must include that scaling factor, that derivative, when you make the switch. If you don't, your integration will be incorrect. 2. Wrong choice of substitution. Another common error is attempting to substitute the derivative instead of the function itself. Think back to what we discussed on slide 2, the function derivative pair. We're looking for a composite function, something like f of g of x. We want to substitute the inner function, g of x, with u. Students sometimes mistakenly try to substitute g prime of x, the derivative, with u. That won't work. Always focus on substituting the inner function, the one that's being acted upon by the outer function. 3. Partial substitution. This is a really sneaky one. It happens when you don't completely convert the entire integrand to be in terms of u. You might substitute some of the x values with u, but leave others as x. Remember, the whole point of substitution is to transform the integral so that everything is expressed in terms of u and do. You absolutely cannot integrate an expression that still contains both x and u simultaneously. It defeats the purpose of the substitution and will lead to an incorrect result. Make sure you meticulously check your work to ensure every instance of x and dx has been replaced. So, keep these 3 common mistakes in mind as you practice. Mastering substitution takes practice, and being aware of these errors will save you a lot of frustration. Now that we've covered the process, potential pitfalls, and even a real-world analogy, you should have a solid foundation for tackling integrals using substitution.